Okay, hi everybody. I hope you had a good weekend. This is one of my favorite lectures of this semester. Here's where we're going to unlock the secrets of hydrogen. And what we've discussed so far has been kind of simple, if you will. I think in some ways hydrogen is a beautifully simple object. Right? We found that we have remember we have three quantum numbers which tell us the energy levels. There's n, which can be anywhere between 1 and infinity. Right, we call this the radial term or the principal quantum number. Right, there's an n equals 1, n equals 2, n equals 3, n equals 4. And then within each n, there are angular momentum states that run from 0 to n minus 1. This is total. This is what's called orbital angular momentum. It's the angular momentum, the total angular momentum of the electron arising from the orbit of the electron around the nucleus of the atom. That's why we call it orbital angular momentum. I don't want to call it total angular momentum like we call J with the rotor, with the rigid rotor, because we're going to find out that it's not the only angular momentum in the system very quickly. And there's also this m number, which can be anywhere between minus L plus 1 to L minus 1 L. There are 2L plus 1 m states. Right? And these are like the different p orbitals. Right? If L is 1, so we'll see that means that you're in a p state. Right? And there are 3 p orbitals, so there's 2 times 1 plus 1 states. There's 3 m states for the p orbital, and there are 3 p orbitals, right? The x, y, and z ones, right? And so these are the different angular momentum states for the same for conserved angular momentum. So for L equals 0, no angular momentum, there's just the s. For the L, there's 3 p's. For L equals 2, which is d, there are 5, and so on and so forth. Right? And the only thing that energy is dependent on is n. Right, we saw that depending on the value of L or m, you get different orbitals or different wave functions, right? The different p orbitals and s orbital. But the energy is only dependent on n. So all this is the 1s orbital, if you will. There's only one orbital at n equals 1, just the s. Of course, there are 4 for the n equals 2 state. There's the 2s and the 2p's. And then for the n equals 3, there are 5 d's. And 3 p's. So that's 3p, this is 3d, and 3s. Everything we know above about electron structure. And this just comes out of the math. Right? This is just a natural consequence of treating the electron like a wave and putting it in what's called a central potential. Right? We have an attractive positive charge in the center of our atom. And our electron has some potential energy of attraction around it, and it's orbiting. And we can set the orbit based on the distance, which is n, and the angular momentum, which is L. Right, but the energy is only dependent on, for a hydrogen atom, is only dependent on n. Right, so we have a bunch of states that are all same energy. I'm going to use a new term. I'm going to define this term. When I say states of the same energy, the term I'm going to use for that is what's called degenerate. All right, so anytime you hear degenerate, think same energy. Okay. So the n states are all degenerate. They have 2L plus 1. They have, L squared. N squared orbitals that are all degenerate energy, hydrogen. Okay. Now something you might think about, and we'll talk about this next class when we get to multi-electron atoms, is when we assign electron configurations. Remember way back when we have some number of electrons in an atom and we want to assign the electron configuration, how many are in P, how many are in D, and so on and so forth. And if we think, for instance, for carbon, how does carbon put the hydrogen, how do you put electrons into carbon? Well, you put 2 in the n equals 1 state, right, the 1s2. Then you fill the 2s. And then you put So there's two electrons in carbon. There's 2 electrons in n equals 1, 2 electrons in the 2s orbital, and then you put the remaining 2 electrons in 2 of the 2p's. Right? So for carbon, we know that the way you fill it is like this. In 2p, you put another set here. Right? But notice what I've done is I've set an ordering to the orbitals. I said before we put anything in p, we put them in s. Right? But if they were all degenerate, it shouldn't matter if I put an electron in the s orbital or put it in the p orbital. They're the same energy. Why would it make any difference? If you imagine thermodynamically, if this was a thermodynamic, you have a temperature, right? You're gonna, if you have 10, let's say if you have 100 hydrogen atoms, then 25 will have its, so let's say helium, let's say for carbon, for instance, or if you hydrogen in this case, if you put another electron in hydrogen, there's a 25% chance it could go into any of these orbitals, right? 2s, 2p, 2p, right? It can be in any of them. They're all the same energy. Why is there a preference to go into the 2s first and not the 2p in multi-electron atoms, right? We know these are the rules. These are Hund's rules, right? How do you fill the off-balance principle, how do you fill electron orbitals? And we make this ordering that S comes before P. But why? They're the same energy. And the key point that we'll have to learn is that they start to break apart. The degeneracy is lifted when you have more than one electron. The electrons will start to interact with each other, and that will cause an energy difference between 2s and 2p. So this degeneracy only exists in a one electron system where the electron can't interact with itself. Right? Well, obviously it can't interact with itself. I mean, it can't interact with another one, right? So the fact that when you have multiple electrons interacting, you end up breaking the degeneracy. Okay, so we'll see that tomorrow, but just something to keep in mind. Right, so hydrogen's kind of unique. It has the same structure as all other atoms, but because there's only one electron, the electron's free to do what it wants effectively, and that leaves all the orbitals to be the same. Right, so once we get to helium, you'll see how this falls apart. All right, we'll actually be able to come up with a very explicit set of rules that tell you the optimal orientation of electrons, right? What orbitals do we want to fill first? Right? We'll come up with a set of rules called Hund's rules that allow us to show that this, for instance, is the lowest energy configuration of carbon. Because there's another option. We could do this instead, right? Why is carbon not like that? Well, it turns out that there's a rule that specifies that this is higher energy. Okay, it's called Hund's rules, and we'll define them next class. All right, but that's just something to keep in mind. And I want to talk about that today. The idea that we have this simple model for hydrogen, of all these different states that are degenerate, and when we look at different transitions, I talked about this a little bit, you get different types of patterns, right? You get this Lyman pattern, this Balmer pattern, the Paschen pattern. And they correspond to some spectroscopic transitions that all end at the same final state, right? So the Lymans all end at the ground state, the Balmers all end at n equals 2, the Paschens all end at n equals 3. And you can kind of see here, it's probably far away, Bracken, which is everything ends at n equals 4. Right? And when you do this analysis, you get these beautiful repeating patterns, like so. This is increasing energy and decreasing wavelength. Again, the Lymans are the highest energy because there's the biggest gap between the upper states and the final state here for the Lymans. And then as you start to get closer to the higher and higher energy, the spacings get smaller and smaller, which means that the higher energy transitions, the ones that go into the third excited state or the fourth excited state or the second excited state, the Balmers and the Paschens, those transitions are at lower frequency or a longer wavelength. Right? In fact, the Balmers are red, which is why I colored them red. I really shouldn't color them red. But my point is that this is the interesting about spectroscopy is that we're actually looking at higher energy electrons or higher energy systems here, but because the spacings get smaller, the higher energy spectrum, for some reason, is on the lower scale, right? So it's at longer wavelengths, lower energies, right? So hydrogen somehow has a reverse spectrum. What you expect? You would expect that more transitions between excited states would be at higher energy, but in hydrogen, the higher energy transitions are at lower frequency, and that's because the energy goes of 1 over n squared, not n squared, like the particle in the box. Particle in the box would be the opposite case. particle in the box would have the higher energy states further away at higher energy or shorter wavelength, and the low energy states would be at longer wavelength or lower energy. All right, so the hydrogen has like a inverse spectrum. Atoms have an inverse spectrum because of this 1/n² dependence of the energy. Okay, and so the reason why I drew these is because I want to throw a wrench into this analysis. Right? So, and this is one of the powerful things about spectroscopy is that, as I maybe mentioned before, I really drove this home in the other class, but I'll mention it again. The morphology of the spectrum, of hydrogen spectrum, and how where the lines show up was determined before anyone understood how hydrogen worked. Right? The electron hadn't, Lyman and Balmer existed before the electron had even been discovered, much less anyone understood quantum mechanics. Right? They didn't have a theory that predicts this. Rather, the theory arises as an empirical fit. Right? It comes from empirical observations for them to kind of backtrack what the structure of the hydrogen atom is from the spectrum. Right? That's one of the reasons why spectroscopy is so powerful, is that spectroscopy and then physical reality are directly connected, right? And spectroscopy in some ways is, in fact, this is what my PhD advisor always said, spectroscopy is applied quantum mechanics. Right? It's the purest form of experimental quantum mechanics. Because what we're doing is we're using light to an electromagnetic field to interact with a fundamental electromagnetic interaction, which is the electron and the proton, and you get unbiased results from it, right? If you know your frequency of your light and there's an absorption there, then you know the molecule is absorbing that light, right? There's no ambiguities about it. So people understood the power of this, but they didn't understand the underlying theory. So everything was, all atomic spectroscopy for the first 19th century up until about the 1920s, 1910s maybe, was all empirical. All empirical. So it was a miracle that people came up with theory and realized, came up with the actual theory of the hydrogen atom and showed that the empirical theory is correct. But these things were only done because that's what they saw. There was no understanding of the underlying physical theory. What I want to do today is to motivate our discussion today, is to look at a very specific transition of hydrogen, one that's been studied for a long time. It's this Balmer line right here, which is called the H-alpha line. The H-alpha line is the n equals 3 to 2 transition of hydrogen. And the wavelength of it is in the red, 656.28 nanometers. Right, so there's a red emission line in hydrogen. It's quite an intense one. And it's this n equals 3 to 2 Balmer line, or the Balmer alpha line, if you will. Okay, so very well studied. It's been, this Balmer line, again, has been well studied for hundreds of years because even though it's not what you call the fundamental transition, right, the n equals 2 to 1 transition, right, this would be the first excited state, if you will, first excited transition, that lies at about 100 nanometers in the UV. And it wasn't until the 20th century that we had ways to really accurately measure UV radiation or detect things, like have filters for the UV, right? So to take a picture, right, the way that these were done was you take a discharged lamp of hydrogen, or you go look at the sun or something like that has hydrogen in it, and then basically apply a diffraction gradient or a prism to split the light out and look for the absorption lines. And we really couldn't do that in the UV until the 20th century. So the Balmer series was studied heavily at first because it's really easy because it's in the red, right? We just need visible light and a prism to be able to measure the Balmer lines. So this main line, the n equals 3 to 2 transition, the H-alpha line, is a well-studied line. It's a very intense line, and has been seen for hundreds of years. And so throughout the 20th century, or for the 19th century, people looked at that line, saw it in the sun, saw it in the stars, saw it in their discharge lamps, right? They understood that hydrogen is everywhere because anywhere you look in space, you find this line, any sort of condensed gas. But then as technology got better in our resolution, got better in our spectrometers, right? How finely can we measure wavelength, right, as that starts to improve? What they found was shocking or surprising. So the H alpha line, so the old spectrum, if you will, of the H alpha line, it's kind of a broad, I'm going to call this old. Let me call this old. A broad line centered at 656 nanometers. I like that. Right, so this is an old spectrum. Every time they took a picture of it, they see this broad hump here. And then as our diffraction gradients got better, as we were able to measure, as we start to be able to gradiate our wavelength measurements more and more finely, right, so you can take smaller and smaller steps. So around the 1910s, people started looking at hydrogen with these new fangled technologies, fancy diffraction gradients and stuff. And what they realized is that this isn't just one peak, but rather when you look at this peak, there are two peaks that are equal intensity. And they're separated by, I don't remember the exact number, I'll tell you in a second. Yeah, very, very small. I forget exactly what it is off the top of my head, but it's on the order of 20 wave numbers. It's a very small splitting. So the whole width of this line is probably about 10 nanometers. And so that's a spread of about 10 nanometers would be about 1,000 inverse centimeters. So you have actually it's a much smaller splitting than this. It's actually more like this. Like this. So in fact, it's this is really dirty. Let me clean it up and draw it again. So you have one line that looks like this. And I'll draw the other component of a different color, like this. You have this very small splitting here. Right, there are two lines there. Okay, so new measurements show that there's a doublet there, right? Which means that the transition between the n equals 3 and the n equal 2 states, and if there's a doublet, that means that there must be states in either the upper level or the lower level that are slightly different energy. Right? The way that you would get this, for instance, is if the n equals 3 line splits into two. And you have one transition that's slightly higher frequency and one that's lower in frequency, okay? These aren't the scale. But the idea is instead of seeing one line, which would explain this red, you instead see, well, I'll color them based on the colors that I have here. One that's green at higher energy and one that's lower energy as well. All right, so this would be the doublet splitting. One of the states is split into two. Okay. And unfortunately, at the time that this was detected in the 1910s, there was no explanation for this splitting. Right? This was new physics. Right? It showed that we didn't really have a complete understanding of the hydrogen atom. Right? That there's something more going on at a finer resolution. In fact, what they call this, not surprisingly, is called the fine structure. Right, that there is some very small, that the states of hydrogen are split very finely, very small gradation. Right, this is big energy, big delta E, and this is small. This gap here is small. Right? This isn't the scale, right? But maybe it looks more like this. Like that, right? Something like that. what we're seeing is this transition and this transition. Something like that. Okay. And the question is where's this cause? What's causing this, right? As far as we know, we've understood the physics of hydrogen just fine. We've put an electron around a proton, let it orbit, right? We talked about the angular momentum of it, right? We've defined that all as carefully as possible. And if we look at the raw spectrum of hydrogen, it matches our theory exactly. But there must be something we're missing because this is not predicted. It's new physics. And the solution to it is rather subtle and actually very beautiful. We've missed another, and the trick, the thing is that we've missed another component of angular momentum in our system. Right? We haven't accounted for one we've talked about. Right? So we've let's think about the physics we've accounted for in the hydrogen atom, physics of hydrogen. We have the electrostatics, attraction, right? The electrostatic attraction between the proton and the electron. The magnitude of angular momentum for the electron, and the direction, LZ. Right? So we've defined as much as about the angular momentum as we can in electrostatic attraction, but what this is telling me is I'm missing something here. I mean, there has to be something else going on in hydrogen to cause that splitting. Anyone guess what we've forgotten that we've talked about already that we know is a factor in the electron and the proton, but hasn't been discussed yet? What have we not accounted for?
Spin.
Yeah. We haven't accounted for spin yet. The electron has a spin of 1/2. There's another angular minimum in the system. So let's think about that for a second. Now I'm going to bring my vectors back again. All right, so here's my vector axis. Here's my proton. And I'm going to attach my electron to it. Some distance r. Right, and we know if we apply a force in this direction, if the momentum of the electron is that direction, then the angular momentum L is the cross product, which means it comes out of the board. Like so. It's out of the board. All right, so what I'm going to do is I don't care about the distance and the momentum, I just care about the angular momentum. So I'm just going to move my vector system around so that it's centered at the electron. And I'm just going to draw my angular momentum vector in some direction. All right, so let's say my angular momentum is in that direction. That's the orbital angular momentum of the electron. Okay, that's just the electron orbiting. Okay? So my electron's down here. All right, and this is its electric force in this direction. Or this is the momentum in this direction. So now, but the fact of the matter is that there's also spin. All right, so we know that L squared times the wave function of hydrogen gives us h bar squared L plus 1. And if we take the spin squared of the electron or the hydrogen, is also h bar squared times s plus 1, where s is 1/2. Okay, so because the electron has a non-zero spin at all times, the total spin, or the magnitude of the spin of the hydrogen atom, or the electron, let's just say the electron, is going to be h bar squared 1/2 times 3/2, which is 3/4, right? 3/4 h bar squared, right? So there's always some residual spin angular momentum, right? No matter what state the electron is, it will always have a angular momentum vector or spin angular momentum vector that has length squared of h bar squared of 3/4. 3/4 h bar squared. Okay, so that vector is always there. But of course it can be pointing, and so I can just write it. I can just draw it next to our vector here. Right? So we have our electron has another vector that can either be like this. This would imply that the z component is plus 1/2. Or it can be pointing in this direction, right? Where sz is equal to minus 1/2, right? You can remember that for a 1/2 spin electron, the electron can either be spin up or spin down, right? So that means that the vector can either be pointing in the same direction as the angular momentum in this case, or be pointing against it. Okay, so those are always there. Well, so we have the important thing is we have two vectors for angular momentum that are, one's always there. Again, L can be 0, but S is always non-zero because the electron is spin 1/2. It's always 1/2. And they both have the same units of length, right? They're both units that are some number times h bar squared. They have the same units, so we can add them together. All right, so let's do that vector analysis now. I'll just redraw it. You don't have to. It's just easier to redraw it. So I'll draw my original angular momentum vector. Right. And then I can either add the minus 1/2 or the plus 1/2. Could be either, right? But there are two options. Right, so the plus 1/2. Let me see if I can just draw it roughly to scale. Could be like this, right? Or it could be like this, right? Equivalently. This is the plus 1/2 and this is the minus 1/2 component, right? It could be either one. All right, and then we take L plus S. We add the angular momentum together. And what do we get? Well, we get the resultant vectors are now at slightly different lengths, right? We could get a new angular momentum vector, L plus S minus, if you will, or L minus S, like that. Or we could get one that looks like this, L plus S, like that. Right, so when you add, so what that means now is that there are two options per L state for S equals 1/2. There's L plus 1/2 and L minus 1/2. Okay? Now the question is, do these have different energies? Right? In order to have a doublet, these have to split. Right? And we can think about this. All right, so are these degenerate? Right? So we have a wave function whose total angular minimum, which we'll call J, is L plus 1/2, and one where it's L minus 1/2, right? Do these have different energies? Are these degenerate? Well, let's think about it physically. All right, and this actually comes from the textbook, and I think it's a really, really nice argument. So let's think about, I'm going to draw my angular minimum vector in this direction. Right? And then what we're going to do, if angular minimum is in that direction, then that means the electron is orbiting like this, right? Right-hand rule means it's curving around here. So the orbit of the electron, classically, looks a bit like this. It's kind of out of the board. Let's see if I can draw that, something like this. Okay. And so the electron, if the angular minimum is that way, the electron, which I'll draw right here, is orbiting in this direction. Okay, and then we have L, but now we need to include S. Right? So S is again the electron orbit, the electron angular minimum. So S could be in this direction. The net force is L plus S. All right, so net equals L plus S. That's not, but net. Net angular minimum is L plus S. But we also have another option. Right? Let me just draw the same thing. There's my axis of rotation for my electron. Right? There's my electron. And there's another option, which is S goes in this direction. Right? So the net, or let's just call that J. I like total. J equals L plus S, and J equals the absolute value of L minus S. Let's take the absolute value. Right? And let's remember that this is an electromagnetic interaction. Right? We have an electron, which is a charged particle, orbiting. We have a charged particle orbiting a central point, which generates a magnetic field. This is Maxwell's laws. If you take a charged particle and you spin it, you rotate it, it creates a magnetic field. Right? So this electron has a magnetic field. Right? It's got a magnetic field as it orbits. This is my magnetic field gradients, just kind of drawing that magnetic field. And now we have another angular minimum being applied, another spinning action being applied to that field. So if we think about the addition, the orbit, the rotation of the electron is aligned with spin if J is equal to L plus S, right? They're in the same direction, right? It's like having a dipole and then another one. They're all pointing the same way. You want everything to align together. And here they're anti-aligned. Right, so in this case, the angular momentum of, if you think about the electron spinning as a part of its spin, here the magnetic field of the electron is spinning in the same direction as the orbital angular minimum. If you think about the electron as a top, right? You have this top that's orbiting a center point, and then that top itself is spinning as well. If spin and angular momentum are in the same direction, that means they're spinning together in the same direction, right? So I'll say that spin is CCW and orbit is CCW. And here you have spin clockwise and orbit CCW, counterclockwise. All right, so these are anti-aligned and these are aligned. And Coulomb's law, our electromagnetism, says that an aligned system, or a magnetically aligned system, is lower in energy than an anti-aligned system. Okay, so these two states, these two options that we have for the electron have different energies, because when they add together in the same direction, plus and plus, the orbits, if you will, of the electron spinning on its spin axis and the electron spinning around the proton are moving in the same direction. They're coherent together. They're not spinning against each other. And then in the other case, they're actually spinning against each other, right? And that's going to be higher energy, right? So this is higher energy and lower energy, right? In fact, this is exactly the same kind of argument that you would make about when you do NMR. When you apply a magnetic field, your proton spins from your hydrogen atoms, they either become aligned with the field or anti-aligned with the field, and the anti-aligned ones go higher in energy, and the aligned ones are lower in energy. Right? It's the same idea, except it's occurring internally inside the hydrogen atom. There's no applied magnetic field from the external, right? This is a hydrogen atom existing on its own. But because the fact that the electron itself has its own magnetic field, and you're generating an additional magnetic field from its orbit, that you end up getting this aligned anti-aligned process, or split. So again, let me write that again. The action of orbiting an electron around a proton generates a magnetic field. And the spin of the electron also generates its own magnetic field. Okay, so the hydrogen atom at this limit is actually the convolution of two magnetic fields. One is the one generated by the orbit, and one is generated by the wobbling or the spin of the electron. Right? And so your fields can either be aligned or anti-aligned, and that splits them in energy. Okay, we call this, there's a very specific term for this. It's called spin-orbit coupling. Right? And the thing is that when you start to add all of these rules we build up for how atoms work or molecules work, when you start to apply spin to them, things start to break down. Spin kind of allows the system to start exploring regions of energy space that it can't otherwise explore. And I'll talk about that as we talk more about atoms. Right, but spin kind of opens up the rabbit hole and starts to make things weird. Right? It's not weird in the sense that we don't expect it. It's just that you end up, the rules that you generate when you don't think of spin start to break. Right? When you add spin, it starts to break rules. All right, but the important thing to note is that the magnetic field from spin, electron spin, is generally small compared to the field generated by the atom. From the orbit. Right, because if you think about it, the spin angular minimum at most is only 1/2. Right, it only is, the projection along the z-axis is 1/2, but L can be 1, 2, 3, 4, 5. So you can imagine if L is 6, spin's still 1/2. And so it doesn't really change the direction of L, the total angular minimum, very much, because you're adding a 1/2 component to a one that's length 6. Right, so what we would expect actually is that as L increases, the splitting will get smaller because the spin only adds a small fraction of extra angular minimum. Right, well, we can see that. We'll get to see that. Before I move on, any questions? Okay. There are lots of things that break because of spin-orbit coupling. All right, and I'll try to illustrate those as we go through the rest of the class. We'll get to molecules and stuff. Spin becomes a problem in molecules. It starts to break rules. You start to get things what are called forbidden transitions. The idea of phosphorescence, for instance. Things that are phosphorescent only arises due to spin-orbit coupling. Right? These are these kinds of effects of fluorescence and phosphorescence and different types of photo dissociations and different types of interesting photophysics all arise from things that are broken, rules that are broken due to spin-orbit coupling. Okay, because spin-orbit coupling in some ways is the number one rule, number one reason why molecules and atoms don't behave the way you think they do. Okay, it's the biggest. We call it a perturbation, right? And spin-orbit coupling is generally the largest perturbation in an atom or a molecule. All right, but before we jump into how this affects hydrogen, I want to do a little bit of notation, because what we want to do is we want to generalize our idea of spin-orbit coupling so we can talk about it for any atom. Okay, all right, because what's going to happen is that, again, if we have this n=3 state that we talked about, and it splits, this splitting is arising, this is the aligned combination, or so this is the anti-aligned combination, the higher energy one. And this is the aligned one. I want to give them names. I want to be able to identify them. So there's a set of notational rules that we use to describe atomic states that allow us to explain, or at least describe in a notational form, how we describe specific states of specific spin and alignment. All right, the rules are pretty simple. All right, this notation is called atomic term symbols. All right, I'm going to write down the formula for it, and then we'll talk about the different. There's basically 3 indices for this symbol, and I'll talk about the rules for it. Okay, so these term symbols have a generic notation. Where the main part of the label is the L, the orbital angular minimum. There's a subscript J, which is the total. I'll write this in a second, finish up what these are. And then it has a superscript 2s plus 1. That's the multiplicity of the state. Okay, so let me define these. S is the total electronic spin of the atom. For hydrogen, that's 1/2. L is the orbital angular minimum. All right, so if it's an S state, it's 0. There's actually labels for it, and I'll show them for you in a second. We have L is 1, that's the P state. And then there's J, the subscript, which is the total angular minimum. And for most atoms, J is usually L plus S, L plus or minus S. Right, those are the only 2 angular minimums in our system right now. For hydrogen, it's just angular minimum and spin. Right, so total angular minimum is usually the sum of the 2. Okay, and so typically L is written, L notation is orbital notation. So if L is 0, 1, 2, 3, 4, 5, 6, and so on, we generally label these S, P, D, F, and then on from there, H, I, and so on. Right, these are where these come from. Why they're called this, we had this conversation last year, Sean, do you remember that, why they're called SPDF? I don't remember exactly what they're called. Why? I like to think of it as simple, I forget what P stands for. Simple, I forget P, diffuse. I know that's what they're standing for. I think it's simple, principal, diffuse, and a fucked in the head usually. I think that's usually what I call it. It's totally yeah, sharp. Yeah, sharp, what was it? What was P?
Sharp, primary, diffuse, and fundamental.
Sharp. I have no idea what they call, why they call them that. These are old terms. and so on and so forth. Sharp, primary, diffuse, and fundamental. Yeah, I like to think sphere, I don't know what you want to call it. Diffuse, I always call them diffuse, and then, font for F. But anyway, so we typically don't label L by a number, but rather by the letter, right? And I'll give you some examples in a second. Okay, and then for a spin 1/2 hydrogen atom, 2s plus 1 is always 2, right? Because s is 1/2, right? And then J is the sum. Okay, so let's use this idea of adding spin and removing and adding spin to angular minimum and see if we can come up with a set of new states. Right, so let's start for n equals 1, for instance. Right, we know that this state, so let's think about the characteristics of this state. Of course, we know that this is the 1s orbital. Right, so what does that mean? That means L is 0. S is 1/2. And so that means J is either, the J is 1/2, right? So it can either be 0 plus 1/2, the absolute value, or 0 minus 1/2. All right, but these are the same value, right? This is 1/2 and the absolute value minus 1/2, which is 1/2. Okay, so what we call this then, this state is the 2s 1/2 state. Okay. Again, spin is 2, so 2s plus 1 is 2. Spin is 1/2, sorry, it's 2s plus 2. We call this a doublet. It's s because it's an s orbital, there's no orbital angular minimum. And the total angular minimum is 0 plus 1/2 absolute value, so it's 1/2. Okay. Right. If you think about lithium, for instance, lithium has a filled valence shell, right? It's 1s2 and it's 2s1. Right? Its ground state, so lithium, the 1s is completely filled. You know, so 2s, 1 in that one. Well, let's think about the total. Let's think about this again. L is 0 here. S is 1/2, and J is 1/2. Right? So this is also a 2s 1/2 state. Right? So the question is, how do you tell them apart? Right? So they have the same identity in terms of angular minimum, right? They have the same term symbol, but they're in different principles, right? This one's in n equals 2, and this one is in n equals 1. So typically what we do is we write another 2 here. Right? So this is the 2s 1/2, and this would be the 2s 1/2. Right? So typically we add an n to it as well. I'll write that here, n. Right, just so we have a way to determine ambiguities. Okay, but let's notice something very interesting about the n equals 1 state of hydrogen. It doesn't split. Right? We would imagine that it splits, right? Because there's a sum and a difference of adding, right? There's L minus S and L plus S, right? The aligned and the anti-aligned states. But if we think about it, this is going to be 0 plus 1/2, and this is equal to 0 minus 1/2. Well, you can't have a negative length, right? So we have to take the absolute value of our term, right? And they end up having the same J, 1/2. So both of these states, when we label them, are 2s 1/2, 2s 1/2, right? Which means that they're degenerate, right? They're the same. They have all the same states. They have all the same quantum numbers. They're n equals 1, J equals 1/2, L equals 0, and spin 2s plus 1 equals 2. So these are degenerate. So the n equals 1 state doesn't split. Let me make a table. All right, so we can just start labeling this. we can start making a list. Right? So states. And then term symbols. Right, so we have the n equals 1, and all we have here is the 2s 1/2 state. Or that's n equals 1, 2s 1/2. Right, that's it. There's just one state. Right, so this doesn't happen. Now the interesting thing is that this does happen. The energy of the state actually lowers a little bit because that spin's still being added, and they add in a aligned way, and that's actually favorable. So the actual state is actually shifted slightly, but the state which would appear higher in energy doesn't appear. Right, so if I were to draw this, so here's our initial guess. Right, this is what happens, right, when we go to, this is hydrogen, and this is our fine structure. Okay. All right, so we've already solved n equals 1. So let's go to the next n equals 2. All right, we know there are 1, 2, 3, 4 states. Right? There's 3 p's and 1 s. All right, so let's do the s orbital first. Right, and of course the term symbol is exactly the same. L is 0. L is 0, so J is 1/2. And spin is 2. It's still a doublet, a spin doublet. So there's going to be a 2s 1/2 state. Right? Nothing happens. And then we have the p's. Right? So now the 2 p's. Right? What do we have here? Well, we have L equals 1, S equals 1/2. So J can either be the absolute value of 1 plus 1/2 or 1 minus 1/2, which is equal to 1/2, or sorry, 3/2 and 1/2. Now we have 2 states. Right, so now what we have, interestingly, we have a 2p 1/2 and a 2p 3/2 state. Okay. P 3/2. Okay, so we know that the highest energy state has to be the 2p 1/2 because this is the anti-aligned state. L and S are pointing in the opposite directions. So this is 2p 1/2. All right, but now what's the difference? Now the question is, we also have a state that's S, that's also a total angular of 1/2. Right, but we know that the difference between S and P in a hydrogen atom are the same energy. Right? Remember, they're all the same energy. Right? So in terms of L, these aren't any different, and in terms of J, in terms of L, they're the same energy, and in terms of J, they're the same energy. Right? So in fact, this state is doubly degenerate, and a 2s 1/2 sits right next to it. Right? Whether they're split or not, we don't know. But what we say is that energy does not depend. Energy depends on J, not L. So these are still degenerate. Right? So we have 2 states sitting there, and then we have this 3/2 state, which is the aligned state, where the S and the L are in the same direction. That's a good thing, and so that means it's down here. 2p 3/2. Right? So in fact, remember that this transition is the Lyman alpha line. And in fact, what we predict is that the Lyman alpha line should be a doublet. Right? There should be some transition here. This is the 2p 3/2 to the 2s 1/2 state at some energy. And then there's this one, which is the 2p 1/2 to 2s 1/2 transition as well. So Lyman alpha should be a doublet. You can look it up, but in fact it is a doublet. It's very small, it's very, very tinily split. You have to have very high resolution spectrometer to see it, but they are split. Okay, and we can keep going, right? I'll just quickly do the threes, just to give you a sense of how the math works, but again, it's just addition. So here we're at n equals 3. We have 1, 2, so we have 3 P's, we have a 3S, 3 P's, 1, 2, 3, 4, 5, 3 D's, 5 D's, 5 3D's, excuse me. They're all the same energy. And so let's do this analysis again, the same analysis as we did before, n equals 3. Let's do the S state, that's going to be 2S 1/2, right, nothing different. The P states are split into 3/2 and 1/2. Right, we can add or subtract. And then there's the D states. And so that's going to be, well, let's think about it. So for D, L is equal to 2, S is equal to 1/2, and we're going to have, we can have 2 plus 1/2 and 2 minus 1/2, which is 5/2 and 3/2. Okay, that's all their options are. So the system splits into these 5 states, and the lowest energy turns out to be the D. And then there's the P, 2P3, oh sorry, 2D, okay, so actually let's think about this. There's actually 2D states, so there's the 2D, we'll talk about these rules, but it's 2D 5/2, the 2D 3/2, and then 2P 3/2, 2P 1/2, and 2S 1/2. Right, so in fact there's a big lump, the n equals 3, instead of having 8 states all the same energy, we actually now have 5 states with different degeneracies. This one has degeneracy of 1. This should also have a this has a degeneracy, let me think, 3, 3, let me think about this for a second. So that's 1, 1, 2, 3, and 2, I think that's right. I forget exactly what the degeneracies are. But it splits into 5 states of different energies. Right? And this can keep going and keep going. Right? And in fact, as you go higher and higher, the splitting gets smaller and smaller, because as L gets bigger and bigger, the influence of S doesn't really change it that much. When L is 10, 1/2, plus or minus 1/2 doesn't really change anything minimum much, so the spacing is quite small. But you can see now we have a very much more complex spectrum to deal with. All right, and now the question might be, which is a question we'll answer next class, is why are the orderings the way they are? Okay. And so we'll come up with Hund's rules. Something called Hund's rules is a set of very, very specific rules that determine how the different energy levels space out, which ones are lower energy than the others. But anyway, so this gives you a really, really interesting perspective, right? That hydrogen in some ways is more complicated than we imagine. What I want to show for the last 10 minutes is kind of an aside, right? Because in fact, it doesn't end there. Right, this is one of my favorite stories. Right, so this fine structure was seen in the 1910s and verified experimentally or theoretically later once we understood the hydrogen atom. This all made sense. But let's go back to this 2s 1/2s state right here. All right, let's just go back to the simplest idea, simplest state. Right, what we've predicted is that with fine structure, this is our basic theory, and this is our fine structure prediction, is that n equals 1 should have a single state that has term symbol 2s 1/2. Okay. But now we have to consider something else. What happens now? Again, let's remember that we have a proton and electron here, right? And this has some spin axis, some angular minimum, right? And that's how we get the spin orbit coupling, whether the spin is against or with the angular minimum. Right? That's how we get the spin orbit coupling. But we've forgotten something. The proton is also spin 1/2. Right? It can also have an angular minimum. So in fact, let's consider that. So let's do our J, which is going to be the orbital angular minimum, plus the spin of the electron, plus the spin of the proton. So this is L plus absolute value of L plus or minus 1/2, plus or minus 1/2. Right? We have an extra angular minimum to add, right? Because now the proton's wobbly. It's always wobbly. And so that means now that J can either be, I think so. If L is 0, you can either have J equals 0 or 1, right? Because you either have, so L is 0 for the S state, so you have 1/2 plus 1/2, which is 1. You can have minus 1/2, which is absolute value 1, or you can have 1/2 minus 1/2, which is 0, right? So J is either 0 to 1. So in fact, what we predict is that due to the spin of the hydrogen, of the proton, that this line should split into 2. This is what we call hyperfine, right? So what we've done now is we've done angular, what we have is just angular minimum. Then we've added the spin of the electron. And now what we've done is we've added the spin of the electron plus the spin of the proton. So in fact, we predict that the n equals 1 state is actually a doublet. In fact, all of these lines are doublets. Actually, they might even be more than doublets, right? Depending on how we can add the numbers together, you might get multiple states. Right, now the question is how big is that splitting? Okay, so let me just give you a comparison. So if we look at the splitting between these two states and n equals 2, right? We have a 2p 1/2 state and a 2p 3/2 state. I actually think I got the orders wrong on these, but that's okay, don't worry about it. So n equals 2, we have these two states here, right? It's these right here. These are the ones that the p's and the s's split into. Of course, I could write 2s 1/2 here as well, and it would be the same energy. And the splitting between these states is 0.3659 wave numbers. It's a fraction of a wave number. All right, so the wavelength of this splitting is 1 over that converted to nanometers. So it's about 3 centimeters. It's about 3 centimeters, which is, how many nanometers would that be? 7. A lot. It's on the order of, let me think about it, 30,000 nanometers, right? It's very low energy. Right, remember that the thing that's being split here, this right here, right, this line right here is at, the wavelength of this is at around 100 nanometers. Right, so this splitting is 100 nanometers, and this splitting between the two split states of the n equals 2 state is on the order of 3,000 nanometers, right? It's like 30 times smaller of a splitting. Right, so in fact, when I should write this, I'm actually not doing it at scale. It really should be something like this. Right? Just a tiny, tiny little split. Right? That's the kind of splitting we're talking about here. Right, so the splitting is very small. So what that means is that this splitting, the change between the basic hydrogen n equals 1 state to the one that's fine structure where you add the spin electron, this shift is about half a wave number. Very small change. And now the question is, well, let's say it's on the order of a wave number. Maybe that's fair. Yeah, well, on the order of a wave number, just to be fair. Now the question is, what's this split? Right? So basically the idea is the spin of the electron changes the energy of the 1s state by about a wave number, maybe 10 at the most. Very small change. So the question is how much does the proton, when we add the proton spin, how much does it affect the energy spacing? Or how does it change the energy? And it turns out that this splitting, the wavelength is 21 centimeters. That's a frequency of about 1.5, it's about 1.5 gigahertz, which means an energy of, let me see, 0.05 wave number. So it's about 20 times smaller. Right, so this splitting is on the order, this is an infrared splitting. So you could detect this in the IR, pretty far IR, you could detect in the IR. And this one is radio, or microwaves. Right, so we're talking about very, very small splittings. Remember, the splitting between the n equals 1 and the n equals 2 states, right? This is 100 nanometers, right? This is ultraviolet radiation. This splitting is infrared. And then the splitting of those lines from hyperfine, from the proton spin, is on the order of a radio communication. Right? It's actually lower energy than the microwaves in your microwave oven. Right? That's twice this frequency. Right? So we're talking about very, very small splittings. Right? And so what this tells you is that if we were to order, right, that from biggest to smallest, the biggest, of course, is the magnetic field of the H atom as a whole, right? The idea of an electron spinning around a proton, that generates a magnetic field. And then the magnetic field of the electron itself, and then the magnetic field of the proton. It's not surprising that the magnetic field of the proton barely contributes or perturbs the spin of the electron. It's a very, very small effect. And that's because the proton's really far away. Right? If you brought it closer together, the splitting would get bigger. In fact, that's what you see. As you get to higher and higher, bigger and bigger atoms, we'll look at this, as the nucleus gets larger and you get more electrons, the spin-orbit coupling gets larger. Right? The more spins, the more electromagnetic interactions you have, the bigger the coupling is, or the bigger the perturbation is. Right? So in some ways, this is the smallest limiting value. Right? It obviously gets bigger and bigger. So the magnetic field of the hydrogen atom as a whole, again, that's just from the orbit of the electron. Right? But then the electron itself generates its own magnetic field because it spins due to its spin, and the proton does too. Right? So you have to consider all three of these. Right? And what that leads to is that you get a fine structure splitting from the spin of the electron, and then another splitting from the spin of the proton. And in fact, if you take a radio telescope, so for instance, one of the big radio telescopes like the one in Puerto Rico, Arcebio, or the ones in New Mexico, JVLA, you can point them at a star, at the sun, whatever you want to look at, a galaxy, and set the frequency to 21 centimeters, the wavelength 21 centimeters, and the whole universe just lights up. Right? Because all hydrogen atoms have this special splitting. Right? There's lots of hydrogens in the 1s state. Right? Lots of neutral cold hydrogens. They're not doing anything interesting. But you always have some that are in this lower energy state due to the splitting, due to the magnetic fields, and one that's in the higher state, right? And when you get that, you can actually look at absorptions in space or in any sort of source, hydrogen-based source, and you can see things that just light up when you shine 21 centimeters at it. In fact, you can take a DirecTV dish, and if you set it up right, you set it up so that it detects at 21 centimeters, you can actually get a spectrum of the sun or of the galaxy just by shining your telescope around at 21 centimeters, right? Because hydrogen is very bright due to this splitting. It's a very important splitting for astronomy. Right? And so you can imagine that as you get to higher and higher L's, when you're in the D's, these start to split like crazy. Right? Because D is 2, you have S 1/2. For both the electron and the proton, you've got lots of ways to add and subtract those numbers together, so these D states split into a lot of states, hyperfine states. Okay. Unfortunately, I had one more to show, but I don't have time for it. I wanted to talk about one more splitting in hydrogen, but we'll talk about it on Wednesday, kind of a side effect. So I'll recap this on Wednesday again, and we'll look at how this affects bigger atoms. Right? We'll move to helium. And we'll see how these rules change for helium, and we'll be able to come up with some more rules to predict spectra and the states of these atoms. Okay. One more thing, I will post a set of practice problems that you guys do not have to turn in, but you can for extra credit over spring break. And I plan on distributing the take-home exam the Wednesday after break. All right. Other than that, I'll give you some more details later. Anyway, have a good day, guys.
Have a good day.
Thanks. You too.
I'm going outside first.
Yeah, you too. Yeah, of course. Let me stop my recording real quick.